Welcome to Dr. Jed's continuing calculus series. Today's lesson is section 5.3 from Rogowski. It's got an auspicious title, The Fundamental Theorem of Calculus. Well, actually, they call it Fundamental Theorem of Calculus Part 1, because 5.4 is Part 2. So I guess we're doing the first half, but we're doing the better half. We'll talk about what it is, and then we'll do examples. That's all there is to it. So what is the fundamental theorem? Well, you may have noticed yesterday's lesson, we talked about the area from a to b. The integral from a to b of f of x dx was the area underneath f of x. This notation looks very much like the antiderivative notation we had in section 4.9, and that's on purpose. Because the fundamental theorem of calculus says, if f of x is a function, and capital F of x is an antiderivative, it doesn't actually matter which one we pick, on the interval a to b, then the area, the integral from a to b of f of x dx, is the difference in the antiderivatives at the endpoints. So this endpoint first minus this endpoint. The reason for this is, suppose we take a curve. So here's the function. We want that area. Well, each time we're adding on a little bit, if you think about mini rectangles, there's a tiny, tiny narrow rectangle. How tall is it? Well, its height, if that's x, its height is f of x. And okay, it's not actually a rectangle. It's kind of got a little curvy part on top. But let's ignore that for the second. How wide is it? Its width is dx. So this is saying the sum of all these f of x dx's is the area. And that's true. Now, what's the derivative of this? Let's take a function. Let's keep going this way. Now, how much does the area change if I move over a little bit? If I move over a little bit, it's adding on an f of x dx component. That's the extra little bit. Now, take the difference in f of b minus f of a. If these two are close, and you're going to get that. Now, divide by delta x, you're going to get that. I don't know if that made a lot of sense, but basically what you're saying is, if you keep adding, a little tiny bit of adding, the rate of change of adding is actually that function. More importantly, this allows us to compute. So whether that makes sense or not, this is how it's done. The integral from a to b of f of x dx is f of b minus f of a, where these are the capital F's, the antiderivatives. So, what is this notation? It's a shorthand for this. This is how you usually write it. Because if you're going to do it two places, you don't need it here and there. You just write it there and then you compute it out. Let's do an example. This is the example from yesterday's lesson. We computed this. It was 30, I believe. But what we need to do is figure out what's an antiderivative of this. Remember, antiderivatives go backwards. So this antiderivative would be 5x plus antiderivative of 2x. There's a rule for that. It's going to be x squared. And you evaluate from 1 to 4. Or actually, you evaluate at both places. So at 4, this is 5 times 4 plus 4 squared. At 1, this is 5 times 1 plus 1 squared. So we get 36 minus 6 is 30. And there you go. This is probably easier than the way we did it yesterday. Let's take a look at another case. This is how we're going to do it. Let's take the integral of cosine of x dx from 0 to pi. This is also one we approximated with rectangles, and we said that it made sense that this one, I think this one should be 0. Well, how do you do it? We need an antiderivative for cosine. Well, you should know the derivative of cosine is minus sign, but the antiderivative isn't. The antiderivative is the positive sign. This is how you do it. 0 to pi. Put them there as the limits. That means we want this here minus this down here. So this is the sine of pi minus the sine of 0. And if you're not sure of your sines, if you don't know your sines from your cosines and so on, you plug in your calculator. assuming you're in radian mode, which remember that's what we always are in this class. Sine of pi is 0. Sine of 0 is 0. This area is 0. This is how fast and how easy it is. Okay, maybe the function gets messier. Speaking of messier, let's do a messier function. 1 over x dx. Antiderivatives, if you remember. Well, if you think backwards in terms of derivatives and antiderivatives, what function has 1 over x as its derivative? It's the natural log of x. We're going to run into some troubles, though. If we're talking about actual area, well, first of all, we're talking about functions. Put a minus 2 in here. The natural log can't have a minus inside of it. It causes error. Not sure? Try it out. But that's true. But if we're talking about area, from minus 5 to 5, minus 5 to minus 2, I'm sorry. 1, 2, 3, 4, 5. We're talking about something that looks kind of like this. That's not really a problem. It's negative, but remember we're talking about negatives as just negative area. That is an actual area. It should have a value. So if you recall in section 4.9, we said it's not actually the integral of 1 over x. The antiderivative is actually the natural log of absolute value of x. So in this case, it's going to be the natural log of the absolute value of minus 2 minus the natural log of the absolute value of minus 5. Now if we do that, you get the natural log of 2, because the minus sign goes away, minus the natural log of 5. Minus signs combined, you can get a natural log of 2/5. I don't know what that is in decimal form, but it's negative. And it should be negative. This is how you do it. This is the hardest one we had so far, and hopefully it still makes sense. So let's do one more like this. Let's go from minus 2 to positive 2. Well, we've already done this. This is the natural log of absolute value of x. Evaluate from minus 2 to 2, which actually it could be, but there's a problem. Because, let me show you this graph. This graph has a problem. 1 over x has a vertical asymptote at x equals 0. The function doesn't exist at 0. The function, it doesn't exist there, so it can't have an antiderivative there. How could it have an antiderivative if it doesn't even exist? This function does not have any sort of antiderivative over this whole region. Over here, no problem. From positives, no problem. Negatives, no problem. But at 0, problem. This has no antiderivative. And it turns out this can't exist. You could argue symmetry, but you got to be careful. We're talking a positive infinity amount here, a minus infinity amount here. So what you're really looking at is infinity minus infinity, which is an indeterminate. Remember? How do you spell that? Indeterminate form. Infinity minus infinity, depending on how you slice it, could be almost any number you want. And this particular one is very problematic. So we just say the answer is does not exist. Again, this happens because 0 is in that region. That's the only problem. So far, that's the only thing we've had trouble with. Let's do another one. This one's trickier. We don't have any rule for specifically how to do this. We're just looking for an antiderivative of this function. I've written it in a particular way to help trigger your insight. So think about that for a second. What am I looking at? This is supposed to be the derivative. What rule? What rule did we use to get that derivative? Okay, well, you could pause. And if you didn't pause, you know. And if you did pause, or maybe you know or don't know. But the truth is here, that's a product rule of derivative. The original function was one thing times another. Because it's the derivative of the one thing times the other, plus the derivative of the other times the... That's the product rule. So its antiderivative is that. What would you do if you didn't notice that? Well, it becomes a tricky thing. Sometimes you can work it out, sometimes not so much. There are tricks. But right now, I'm just looking for clues as to how to anti-differentiate these functions. Anyway, the last step, once you've figured out what the capital F is, you just plug it in. That one's not really necessary, nor is that one. So I'll leave this as 3 e to the 3 minus e. That's a big number. You can compute it, and that's how you do it. The fundamental theorem of calculus just says, if you take an integral from somewhere to somewhere, if you could figure out the antiderivative of this, plug it in, you're basically done. Until next time, this is Dr. Jed.